Okay, algebra. As we know, algebra in mathematics, it is expressions, mathematics expressions. There will be a set of elements, operators, axioms, and postulates. So why this is algebra is important? We used to make symbols and convert their practical problems into a mathematical expression. Then that mathematical expression can be simplified. We can use it to do many things in our daily life. Most likely in algebra that we used to do in mathematics, we used to deal with numbers as zeros and ones. Zeros, ones, two, three. We'll call it decimal numbers. So there will be a set of elements and a set of numbers that we can obtain. So, and the most likely, for example, when there was some analysis in the neutral numbers, the natural numbers. The natural numbers is the numbers from 1 and so on. So there used to be some operators like addition, subtraction, multiplication, divisions, and there was some axioms like distributivity, identity elements, so associativity, all of these from mathematics. We will not worry about it here because we are here in digital logic circuits, so we will focus on something called binary systems, which is only zeros and ones. Then in the algebra here, in the digital logic, will include only zeros or ones, or will be only restricted to binary numbers. We will not worry about 1, 2, 3, or any other numbers, so it will make it more simpler than the mathematics, algebra in mathematics. Algebra in the binary systems has been created by a scientist called George Boolean. That's why the algebra in digital logic is called Boolean algebra, because of the favor of the George Boolean. He had an idea, or try to create an expressions using and operator, or operator and not operator as well. So he tried to create these problems, or we call it algebra, or the binary numbers, zeros and ones, try to make them as simples, then make them connect them with operators, and, or, and nots. So he did some basic functions and tried to simplify it. So then we created something is called Boolean algebra. Then later, this system has been used a lot in academia, especially by one of the students in I'm not sure what's exactly, but in 20th century, it's called Claude Shannon. He uses his science, or the science that has been, or the theory that was done by George Boolean, to be used in real life, in real symbol that we see now. Then created something called Boolean algebra. So again, Boolean algebra comes from the George Boolean. He created a lot of mathematical theories in logic and probabilities. Then he, because in the binary approach that we have yes or no, true or false, on and off, he created these things. So there are some, we call it axioms of algebra structures. So let's assume that we have two sets, or the binary. So we have the addition and we have the multiplication. So the plus and dots, the operators. So we have with this the operation. So if we have x and y belongs to b, b means that a binary, which is 0 or 1. Here now I'm trying to explain some mathematics. Belongs to sets of zeros and ones. Then their addition must be between zeros and ones, and that's normal, that's what we know. Then the same also for their multiplication must be between zeros and ones. It must be bounded between this. And it's associative as well. So whenever we say x plus y between brackets plus z, it's the same as x plus y plus z. This is from regular algebra that we know. Then the same also for the multiplication. X times y times z between brackets is the same as x times between brackets y and times z. And it's commutative, which means x plus y is the same as y plus x. Then x times y is the same as y times x. That's what we know. And that's normal. That's why we call it axioms. Everyone knows it, and there is no need to prove it. I mean, it can be, we already know this. Now, for the identities, we have some identities that we need to know and be aware of. So we have, let's assume 0 plus x, which is the same as x plus 0, it will be x every time. 1 times x, which is the same x times 1, it will be x. Okay, this is well known, but here just I'm trying to explain the idioms or axioms of this. Then here, if we need to have this x plus x bar equal to 1. And x times x bar will equal to 0 with its complements. So this is a must. X plus x bar will equal to 0. How? Let's assume x is 0. 0 plus 1 will be 1. Let's assume x is 1. 1 plus 0 will be 1, right? So this is valid, true. X plus x bar equal to 1. We will use it a lot. And x times x bar will be 0 every time, because 0 times 1 will be 0. And the same time, 1 times 0 will be 0. Okay? Then, did you submit in Canvas? Okay, somebody in Canvas. Thank you. Then, when there is a multiplication, for example, x times y plus z, it will be x times y plus x times z, and that's normal, that's what we know. Here, x plus y times z, it will be, this is something that will be here different, which will be x plus y, x plus z. Maybe these things might look new to us. X plus y times z, it will be x plus y times x plus z. We will use this a lot. Okay, this kind of axioms, we will use, you need to either memorize some of them, and we will go to some other results, or we call postulates. These postulates will be in a table. That table, you don't need to memorize it. It will be included in either in the quiz or in the exam, so it will be provided. So whenever we will discuss the postulate later, it will be fine. But these kind of idioms, you should be aware of them, and you need to memorize them. Actually, I mean, they are well known, all of them, but the only thing that you need to know maybe here, which is something that new to us, that's not applied in the mathematics algebra, but it's applied in Boolean algebra, which is the plus is distributive. So it will be x plus y, then x plus z. These things maybe looks among these 6 idioms, this thing looks new. Okay, Boolean algebra. Again, it is because it has been created by George Boole. Then there is some, in order to do some analysis, it's the same, similar to the algebra that we know, which will be x and y and some symbols, z. But here we will notice that for the not operator, we will use a bar. So you will see maybe x plus y bar plus z. So you will see these kind of symbols donated for the complements of that number. Then in order to do some analysis, there are some postulates has been developed in 1904. So these postulates we need to be aware of. So we have some something related to the operator plus and the operator dots. Most likely in the Boolean algebra, it will include only these 2 operators, the addition and the multiplication. You will not see division, you will not see subtraction. So we can perform the subtraction actually by making the complement, so that's why you will not see subtraction at all. Okay, let me fix the mic. Okay. So we realize that Boolean algebra is one way to, or it's a good way to represent some practical problems. So for example, if I need to have, for example, the garage door is open and the car is on, then and there is no other cars in the streets, so you can leave the garage, drive the garage and go out. So you can make the simples, and instead of making garage and the lights and so on, or like the motor is on or not, you can make it as a simples. So make the simple as the garage door as simple A, the street status if there is any cars or not as variable B, and so on. Then there are some other like definitions. There is something called literal, there is product term, and there is sum term. So the literal is a variable or its complement. So for example, let me assume we have this representation, xy plus z. So the literal, this is literal x, this is literal y, this is literal z. Product term, which is xy, this is a product term. Sum term, xy plus z, this is sum term. And that's it. So these are basically simple. Now, two-valued Boolean algebra, plus operator is very similar to OR operator. So whenever we have 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, in the past we used to make it 10, but here in algebra we will deal it as OR, so it will be 1. So now 1 plus 1 in algebra is no longer 10 as in the past. In the coding is different than algebra. How about dot operator is close to AND, which is 0 AND with 0, 0, 0 AND with 1, 0, 0 AND with 1, 0, 1 with 1 will be 1. So it looks like also the multiplication. So again, plus with AND, dot with plus with OR, dot with and the inverse is with not. So the inverse, x or x bar or which is 0 will be 1, 1 will be 0. We all know this, so there is nothing new. Now we have some properties that you all need to be aware. All of these 9, you need to be aware of it, or because this like 9 properties will not be given. You need to maybe write them in your note sheet, or you need to already well known, so you don't need to memorize anything at all, or just whatever more convenient. So you need to be aware that these properties will not be provided in the quizzes or in the exams. So you should look for a way that you can memorize this. X plus 0 equal to x, this is 0 axioms. X times 1 equal to x. X plus 1 equal to 1, this unit property. No matter what it is, it will be 1. X times 0, it will be 0. X plus x equals to x. There is no 2x. We are with binary. X plus x equal to x. X times x equal to x. There is no square. We are in binary. So x. So you will not see this kind. X plus x bar equal to 1. This complement. X times x bar equal to 0. X bar will be equal to x, which is the involution. So the inverse of the inverse is the same. Okay? Now there is something called principal duality. So this is very important concept, the duality. So we can make the dual expression of this still valid with the axioms. So what does this mean? The duality means the dual expression. You can replace all the plus operators with dots and all the dot operator with plus. And keep in mind that all ones will be zeros and all zeros will be ones. What does this mean? Here we have A plus BC. We need to apply the duality. The duality means any multiplication will be any plus will be dot, any dot will be plus. So multiplication will be addition, any addition will be multiplication. So how to represent this? It will be, here is A, remain as is. Here is, there is addition, it will be multiplication. Here is B, will remain as is. Here is C, there is a multiplication, it will be addition. C, and don't forget to put it like this way. Okay? Then we can make it like A times B plus A times C. Okay? Just make the multiplication. Then we can apply another duality principle. So it will be A, this multiplication will be addition plus B, and this plus will be dots, and here is A plus C. Okay? Does this make sense? Here I'm trying just to give you some tools how to use the duality principle. Now your turn. Try A, B plus C. Try to do the duality. Any multiplication will be addition, any addition will be multiplication. Just reverse this. It will be A plus B times C, right? Then, can we do more? Yes, we can. Let's try to make it as what shall we do? We can make the multiplication like A plus B, A plus C. How did I obtain this? Because there is an axiom, you can convert this to this. Recall this axiom. X plus y, z, x plus y, then x plus z times x plus z. Then after that, we can apply another duality principle, which is, it will be A times B plus A times C. Then we validate how? We validate this. Okay, clear? Any questions? So basically the duality, the AND will be dualed by OR, the 1 will be dualed by 0. This table will be provided to you in the quizzes or in the exams or whenever you need any use to Boolean algebra. This table will be provided to you. So you need to know how to use this table, or like just understand this table. Then we will learn how to use this. So we will see that the postulates, like P for the word postulates, T for the word theorems. So we have, I think here maybe 6 postulates, 8 theorems, and you will see each one has A and B. A is the expression itself, B is the dual. Just apply the duality principle. So for each one, it has its own dual. So for example, A plus 0 equal to 1. The duality of its A will remain as is, then dots, or the positive, the addition will be multiplication, the 0 will be 1, then here equals to A. Then this is the duality. That's how we get it. How to apply about applying the duality into the second one? It will be A, the multiplication will be, addition will be multiplication, AB equals to BA, and so on. So A plus B plus C equal to A plus B plus C, then just make the duality. Then the fifth one, number 5, a plus bc equal a plus b, a plus c. Then whenever you do the duality, it will be the addition will be multiplication, the multiplication will be addition. Okay, clear? Then a plus a bar equal to 1, the duality, the positive will be multiplication, 1 will be 0. A plus a equal to a, here a times a equal to a plus 1 equal to 1, a times 0 equal to 0. They are all based on the duality. A bar will be a, then the same way a bar will be a plus ab equal to a, here a, angle a plus b equals to a, and so on. A plus a bar b equal to a plus b, a plus a bar plus b equal to a times b. They are all based on the duality. So ab plus ab bar equal to a, then here a plus b bar equal to a, here ab plus a bar c plus bc equal ab plus a bar c. It will be a plus b, a bar plus c, b plus c equal to a plus b, a bar plus c. Then the last one, a plus b all bar equal to a bar, b bar. Here a, b all bar will be a bar plus b bar. Okay? So basically, again, you don't need to memorize this table. You need to know how to use this when it is needed. So maybe like during simplification or a proof, or simplify the following expression, or prove this expression equal to this side or equal to this side. How to do this? You can use the theorems and the postulates in this table and make your own simplification. So maybe you will see like a proof or simplify the following Boolean algebra expression. Why we need to do this simplification? Let's assume we have a real world practical problem and we have a lot of complexity on it. If this thing and this thing, let's do this, and if this and this, we will do this. So basically what we will do, we will convert these verbal words into variables, and these variables will be toward expressions. These expressions will be as, we call it algebra, will be represented as Boolean algebra. Now, when this representation is complicated, I can build a circuit, digital logic circuit that can handle it. That's fine. But the problem is, it will be too complicated. It will maybe sometimes cost a lot of using a lot of logic circuits, which means it will cost a lot of money, will consume a lot of energy. So what we need to do, we will simplify this. So our target is there a way to make it more simple and satisfy the same requirements, satisfy the same targets? Then yes, let's do it. Make it simple. We can save more costs. Let's imagine that if we can, a very large expression to do, for example, let me assume that we need to make a traffic lights. And we figure out that the Boolean algebra for the traffic lights is very large. Let's look for a way such that we can simplify it. Can we simplify it more? If we can simplify it using Boolean algebra, postulates and theorems, then that's fine. We can save it. We can reduce it, for example, to the half. When we reduce it to the half, then we can build the traffic lights with half hardwares than in the old one. So what's the advantage? We can save more costs. Then if we are making a production line for the traffic lights, we can save a lot of money on it. So our targets here is to try to simplify the Boolean algebra as much as possible so we can save more money, save more costs. So what we will see now, and like we'll deal with some Boolean algebra equations or representations, and we need to simplify it as much as possible. Sometimes the way that you are simplifying it is different than mine. Maybe you will get some expressions that can be different than any other people. That's why most likely, whenever we will see this in the quizzes or the exams, I will not leave it as an empty or as an open. So maybe you will simplify it in different way that I will get, or maybe you will not figure out exactly how to get the expression. So most likely it will be as a proof. So show me or prove that this left hand side equals to the right hand side. So that's this will be more convenient for me and more convenient, I think, for you as well. So you can show that using these expressions and postulates to get that targets. But in real life, we need to simplify it more and more and more. And sometimes we will realize that using Boolean algebra, it will be kind of consuming a lot of energy, consuming a lot of time. And even it will make us frustrated. We will see this also later. Like dealing with this is not as easy. Today's lecture is one of my least favorite lectures because dealing with this algebra kind of complicated. Now let me talk a little bit about these theorems. So we know like about the postulates. We already discussed about how to use them. So let's talk a little bit about start with some small proofs. After that, we'll go complicate step by step. So show that x plus x equal to x. How can we prove this? We can say that x plus x is actually x plus x times 1. Okay? And we know that 1 is actually x plus x bar. So we can say x plus x times x plus x bar. And we know in some postulates, or like x plus x bar equals to x plus x times x plus x bar. Like some postulates here, which is using this kind of postulate. Then after that, we can substitute it here. It will be x plus x bar. And we know that x times x bar is actually 0. Then it will be x plus 0, therefore it will be x. Okay? This is one way of proving these theorems. Now, prove that x times x equal to x. So it is basically, we will apply similar to what we did before, but with duality. So x times x plus 0, that's what it will be. And we know x times x bar is actually 0. Therefore, it will be x times x plus x times x bar. After that, let's take x as a common factor. It will be x plus x bar. And we know x plus x bar is actually equal to 1. Therefore, it will be x times 1, then it will be x. Okay? Any questions? Now, there is a postulate, or I'm sorry, I'm not sure if it's postulate or theorem, but it says that x plus xy equal to x. How can we prove this? X plus xy equal to x, which means y disappeared. How can we prove this? Basically, take x as common factor, it will be 1 plus y. And we know 1 plus any logic, it will be 1. So it will be x times 1, then it will be x. Because we know 1 plus y equal to 1. Okay? Clear? Now, consensus theorem, which is xy plus x bar z plus yz equal to xy plus x bar z. What does this mean? This means the element yz has been disappeared, like neglected it. So xy plus x bar z plus yz, like yz, you can neglect this. This consensus theorem is very important, and we will use this a lot in our analysis. So keep in mind that you need to be aware of it. Then the same thing can be applied to its duality. So the dualities, you know how to do the duality. Multiplication will be addition, addition will be multiplication. Zeros will be ones, ones will be zeros. So how do we prove this? We can prove it by putting like xy plus x bar z, then plus I'm going to put a new term. I'm going to call it here x plus x bar, then here yz. What I did here it's times 1. 1 equal to x plus x bar, right? That's what I did here. Then we can make the multiplication, so it will be xy plus x bar z plus xyz plus x bar yz. Now we can group something, like some elements. So we can group, we will see this element, there is xy on it. This element, there is xy on it. This element, there is x bar on it. This element, there is x bar on it. So let's try to group them. The first element I'm going to take xy as a common factor. Then it will be 1 plus z. Right? Do you agree with me on this? Then plus the other elements, x bar. Then it will be, I think, x bar z, because z is a common factor as well. Z. So it will be x bar z, it will be 1 plus y. And we know 1 plus any element equal to 1. So as a result, it will be xy plus x bar z. And that's what we got here. Problem done. So these kind of proofs that you need to be aware how to deal with this. Okay? Now in the notes, you will see, let me give you time to write. Next slide. In the notes, you will see some theorems related to exclusive OR. I'm not willing to give it to you, so remove it. I don't want to make it too complicated. Exclusive OR. Now, here is one example. Simplify this expression, or most likely you will see it as proof this expression equals to this one. ABC plus A bar D plus B bar D. We need to show that the left-hand side equals to the right-hand side. How to deal with this? What we did in the beginning is we can look at the term A bar plus D. We can apply the duality for it. Applying the duality, we can take, D as a common factor. Apologize. Take a D as a common factor. After taking D as a common factor, it will be this relationship equation. Then we can apply as a theorem that we know, which is A, B, all bars, those are equal to A bar plus B bar. So what we will do here, we will replace this by AB. Okay? So it will be ABC plus A bar, B, AB, all bars, D plus CD. Then there is another theorem here, which is that we know, let me write it here. X, Y plus X bar Z plus YZ equal to XY plus X bar Z. This theorem, we already know it here. I will apply this one. How we find it? It's already been in the table as well. Let's go back to the table, and you will see it's as X or as Y, which is theorem number 8. Or is it number 8 or number 7? Number 7. So how we do it, how we can do it, again, I figured it out from the table, by looking at the table. Now, we have symbols. We don't have X and Y. What we will do, we can substitute, instead of X, make it as AB, substitute Y, and let's make it as C, and substitute Z as D. So as a result, it will be like this. AB times C plus AB bar times Z, which is here D, plus YZ, which is CD. It will equal to ABC plus AB bar D, which means like this term, it will be like neglected. And that's how we obtain this value. Then we can apply again that we know that AB bar is actually A bar plus B bar. So let's substitute it again here, and we'll obtain this. Then do the multiplication, ABC, A bar times D plus B bar times D. Then we get the solution that we need. Okay? Okay, let's go to the next one. I think maybe today's lecture kind of boring, but should be fine. It will be all right. Now let's simplify this expression. And we need to validate or prove that this expression is actually equal to A plus B. How can we prove that this one is actually really equals to A plus B? Let's start by doing the multiplication here. A times A bar, plus A bar B, plus B, plus A times A, as we know. Then here, A plus B bar. Okay? Is this fine? Now, A times A bar is actually 0. Then plus A bar B. Then we can apply the duality principle here. So it will be BA plus AB bar. And sometimes I don't prefer to use the word BA. I prefer to make it in the alphabet order. So I'm going to make it as AB. Okay? Now, we are not done yet. So what should we do? We can take here A as a common factor. So here 0, we can neglect this. It will be A bar B plus take A as a common factor. It will be B plus B bar. So B plus B bar will be 1. So then it's going to be A bar B plus A. Okay? What else? How can we simplify it more? We have one of the postulate, which is the addition. The multiplication can be, we know that from the ABC. Let me write it in different colors. We know from the theorems in the table, A plus BC is actually A plus B, then A plus C. So here, instead of A, I'm going to make it as A uppercase plus A bar B. It will be A plus A bar times A plus B. And that's what we will do. Then it's going to be A plus A bar times A plus B. And we know A plus A bar is equal to 1. Then the answer will be A plus B. Then problem done. Okay? Any questions? Yes?
When you're swapping out B plus A for A times B, which postulate is that one?
Do you mean this one?
It's near the top. It's at the top in green. You have B
Here?
plus A. Yeah, that goes to AB. And then your A plus B bar goes into AB bar.
Do you mean this one? How?
Yes. Yes, sir.
Yes. So there's a duality principle.
So why can you apply the duality to one side of the equation and not the other?
You can take a term. I take this term and apply the duality here.
Okay. Gotcha.
Okay. Any other question? Okay. Now, let me go to simplify this expression. A plus B bar plus C, AB plus A bar plus C bar. Now, there's something that's you need to know when you apply the bars. Let me explain it to you, then we will apply it here. So when you apply, I'm going to write it in blue color. A plus B, all bars, it will be A bar times B bar. Okay? How about if we have A plus B plus C, all bars, it will be A bar times B bar times C bar. How about AB, all bars, it will be A bar plus B bar. Just make the opposites. When you put the bars above the letters, keep in mind to convert. Any addition will be multiplication, and multiplication will be addition. How about A plus B, C, all bars? It will be like A times, here's A bar times B bar plus C bar. Okay, did you get it? How about AB plus CD, they are all bars. How will it be? It will be A bar plus B bar, put the brackets, C bar plus D bar. Okay, does this make sense? Okay, so you need to be aware how to use, when you put the bar, distribute this, it will be something different. So we'll make it different, like any multiplication will be addition, any addition will be multiplication. Okay, let's see, go to this expression. Oh, let me see, Okay, so let's prove that this expression equals to A B bar plus A bar C. How can we prove this? We need to show that this expression equal to this. Now, let's try, look here, there is a bar. Let's try to distribute this bar on the expression. How? I'm going to leave the expression here, A plus B bar plus C. The first term will be as is. Now the second term, AB, I'm going to make it distributed like this. AB bar alone, and the dot here, the plus will be multiplication. A bar, C bar, all bar. Then, let me keep simplifying. It will be A plus B bar plus C times this expression AB bar, it will be A bar plus B bar. Now here, this multiplication will remain. Then here we have A bar will be A plus, because multiplication will be addition, C bar will be C. Okay, do you agree with me to this point? Is this clear here? How do we apply the bars? Now, we need to do simplification. Let's try to make the multiplication between these two terms. So it will be here A plus B bar plus C equals to A bar times A plus A bar times C plus B bar times A plus B bar times C. Most likely, I don't prefer to use B and A. I prefer to make it an alphabet. Therefore, I'm going to write the A here, because I prefer to make it on the alphabet order. Now, A bar times A is 0. What else? How can we simplify it more? we can do the multiplication between these two terms. So let's do the multiplication more here. It will be A bar C plus A, still multiply A here, A with A, B bar, plus A, B bar C. This is the first term done. Now let's do the second term. Then plus B bar, so I prefer the alphabet, A bar, B bar, C, plus A, B bar, B bar, plus B bar, B bar, C. This is the second term. Let's do the third term, which is C, plus B bar, C, C. Oh, I'm sorry. Let me do it again. C with A, so A bar, C, C, plus A, B bar, C, plus B bar, C, C. Now, we can simplify it more because A times A bar, 0. And here A will be A. Whenever we see B bar will be B, B bar will be B, C will be C, C will be C. So let me resimplify it. It will be 0 plus A, B bar, plus A, B bar C, plus A bar, B bar C, plus A, B bar, plus B bar C, plus A bar C, plus A, B bar C, plus the last term B bar C. Okay? Now we can see some common factors, like here is B bar C, B bar C. And this term is 0. Then we have this term AB bar, AB bar. What else? BC, and we have A bar, A, B bar, C bar. This is the same. A, B bar, C bar, this is the same. So we know x plus x equal to x, so these terms will remain A B bar plus A B bar C plus A bar B bar C, this term already done, repeated, plus A C bar. Is it AC bar or A bar C? A bar C, I think. Yeah. Now we still need to simplify it more. We can look at the other terms by looking at, we have here BC, common, BC, and we have here B bar C. We have B bar C here. And there is a term here, B bar C, that I missed. B bar C here. So we have a term B bar C. So as a result, we can group B bar C together. So it will be A B bar plus B bar C plus A bar plus 1 plus A bar C. Then this term, of course, will be 1. As a result, it will be A B bar plus B bar C plus A bar C. So how can we simplify it? We can look at this equation, this postulate, one of these postulate, which is we know that AB plus A bar C plus BC is actually AB plus A bar C. Therefore, we can apply it in our results as A B bar plus A bar C plus b bar c will be, this term will be removed, so it will be ab bar plus a bar c. As a result, we can apply it to our answer. It will be ab bar plus a bar c, and that's what we need to find. And that's it. Yeah, dealing with this is not fun, but that's how we do the simplification. Like when we do the Boolean algebra, it will take some time, will take some efforts, and kind of headache to do it, to handle it. But we should know how to deal with this using the postulates and the theorems. The last one, which is the most difficult one, okay. It will take a lot of time. Proof this expression equal to AB plus B plus CD. How we do this proof? Okay. Dealing with this will take a lot of time, but let me do it. I have a piece of paper here that I can show it to you. So it will be much easier to follow. So prove that ABC plus ABD plus A bar, B bar, BC bar plus CD plus B bar D equals to AB plus B plus C. So, I'm sorry. The first part, we will take B as a common factor between these two. Taking B as a common factor, then rewrites the same expression and take B as a common factor. It will be AD plus D bar. Then, we know according to theorems, A plus B plus C equal to A plus B, then times A plus C. Therefore, D bar plus AD equals D bar plus A, then D bar plus D. Substitute this instead of this one. Then it will be rewrite the expression and substitutes this theorem that we obtained here. Then we will realize also D bar plus D equal to 1. Then rewrite the expression, D bar plus D equal to 1. Therefore, it will be as shown here. Then do the multiplication. It will be B D bar times AB, as shown here. So after that, by looking at AB and ABC, there are AB common factors. So it will be, take AB as a common factor. It will be C plus 1 plus this expression. Then it will be AB plus A bar, B C bar plus CD plus BD, D bar. Let's take B as a common factor. It will be B A plus A bar C plus CD plus B D bar. Then we can use the formula. We have A plus BC is actually A plus B, A plus C. Then A plus A bar C bar will be A plus A bar times 1 plus C, A plus C bar. Substitute this here. It will be A plus A bar times A plus C bar. A plus A bar is actually 1. Then do the simplification. It will be B times A plus C bar. Do the multiplication. It will be AB plus BC bar plus CD plus BD bar. Then take B as a common factor. It will be AB plus B plus C plus D bar plus CD. Then apply, we can apply A plus BC equal A plus B, A plus C. Then substitute this. We see that this formula, we are using this a lot. CD plus BCD will be CD plus B times CD plus CD bar. Then we will get this formula. Then CD plus CD bar is actually 1. Then after that, it will be AB plus B plus CD. I'm willing to pause this on Canvas, so you don't worry about like missing what I wrote here. Okay, any questions? Okay. So dealing with algebra, especially with Boolean, is not is not easy as we think. Therefore, how can we make the programming if it looks like stuff like this? How we can do it? Therefore, there is something has been created. It's called, that we will talk about it later. It's called canonical forms and kernel maps. These kind of forms and kernel maps will make the life easier and make it much easier. So we don't need to make the this simplification using the postulates or the theorems and doing it manually. This will take so long. So the canonical forms, or we'll call it kernel maps, as we'll discuss later, will make the life easier. So we can do the simplification using some tables and in an easy way, and we can in an organized way. So we can guarantee the way that I'm doing the simplification, the same as yours, the same as someone else. While when I answer these representations, maybe my simplification different than yours, different than your colleague, so it will take so long. So you will see the homework number 2. You can try it at home. Most likely, it will be simplifications similar to this. So you can try these homeworks at home, and I think the deadline will be in June 8th, so you still have some time to do. And the idea of this is just to practice and how to use the postulates and how to use the postulates and theorems in simplification. So the grading of that homework will not be hard. Will not be too hard. So whenever you do some simplifications, it should be fine. Okay, any questions? Okay, let's go to